Hello everyone, I'm William from RX Solutions, and today I'll be talking about CT scanning. So I'll start off with the basics, explaining what is CT scanning, followed by a brief introduction about the company and the products that we offer. Then I'll give a whole bunch of examples of CT applications where it can be used, just some general examples, and then I'll end with a general system demo to show you the flow of how the system works from the beginning till the end. First, the basics. Everybody knows X-ray and CT scanning. So CT stands for computed tomography. What is the difference? In X-ray, it's a radiography mode where you just have one image of the full volume, so you can see certain things happening, but you don't get a perception of the depth of the part. Next step would be to use a bunch of X-ray images and to go to a CT scan. And with the CT scan we get a lot more data. So on the right image you can actually see in more detail. You can take a slice inside of the part and start looking for smaller details compared to a general X-ray image. So next step is to go to tomography mode. It has the same setup, so we have the X-ray source on one side, a detector on the other side. We put the sample in the middle and we make a 360-degree turn with the sample. During this time, as a result, we will get this type of image, so really get a virtual cut of the sample, and you can really use it to do measurements or any other type of control. This is what it looks like in a real machine, so the same machine as we have just behind here. So we have the sample in the middle, a rotation stage, and then X-ray source which is generating the X-rays and which are being captured by the detector on the other side. The images that we're going to create look like this. So we're going to create a whole bunch of these during a 360-degree turn. Then the next step, once these images have been created, is to combine them with special algorithms and calculate it into a 3D model. And so once we have this digital 3D model, we can use this to exploit it to do any type of measurements or to do any type of analysis on the part. So the next step would be to check for porosities, for instance, to do dimensional checks, to compare it with the original CAD model, to check for cracks, so it can be used for different type of analysis. So just to summarize, we have three steps. We have the acquisition as a first step. Next up we have the reconstruction to create the 3D model. And as a last step we have the post-processing, so that means using the 3D data that was created to do measurements, to do analysis on porosities or something else. We see the technology being used in let's say the full life cycle of a product, beginning from R&D side where they're looking for material characteristics. Then later on in the stage for engineering it can be used to check prototypes, to see samples that have had stress loads and so on, to check how they changed without destroying the part. So it's a non-destructive way of analyzing components. Then further on in the production side, it's mainly used for sampling on production lines to see if the first of tools are okay, if the first samples from a new production run are good. Then further on in the life cycle, we see it also being used for parts coming back from customers to check for warranty claims. So the advantage is we don't have to cut the sample. We can scan it in its current state. So because we're not cutting, we're not changing anything to the correct characteristics of the sample. Where do we see the advantage compared to conventional technologies? Especially very small and complex shapes are very, let's say, beneficial to use CT technology, because we don't have to manipulate them during the scanning. We can just put it in the machine, it'll scan them like they are. We don't need to turn them around. So for very small components that's quite useful, and also of course the complexity of the parts is no issue for CT technology. So also the inside of these complex components can be visualized. Anything which is flexible, so we don't need to touch the object during the scan, we can just leave it inside of the machine and it will make the scan. Anything which is transparent, so CT, X-rays, they don't care about the color or the transparency of objects, they just will make the image based on the density of the material. So that you don't need to spray the samples or anything, you don't need to treat them before the scan. Anything which is related to assemblies, so just looking inside if certain components are in the right place, if there's any connections missing, that kind of thing. So in this case this is a phone, scan of a phone, to see different components inside. Then looking internally to objects, that in this case this is a plastic bottle, so the wall of a plastic bottle with different types of layers. And so in this case we can really look at the material properties inside of the layers and measure the different thicknesses of the layers. And then another advantage is that we can use the same set of data to do different type of analysis. So if you want to, in this case, this is powder, we are measuring the powder, so the different grains of the powder. It can be the sphericity, it can be the size, the volume of these of the powder, and at the same time we can look inside of the powder and check for porosities inside of the powder or inclusions, as you can see on the bottom one. So next I'll present RX Solutions and our different products. So we are a French-based company and we are fully focused on X-ray systems. We design and manufacture them in-house in our facilities. We also develop our own software. We are currently 50 employees and we are represented throughout the world by our distributors. So the Sempre Group is our distributor for UK and Ireland. From a customer base, we work in both academic and in the industrial market. This is our product range. So as you can see, we have different sizes. So we start with the EasyTom S, which is the smallest system, which is the one that I have here behind me. So you can see it's, let's say, the size of a big fridge. And this size is capable of scanning parts from 230 millimeters up to 380 millimeters in height. So relatively big samples. If we need to go to bigger samples, we will go to the bigger system. So we have the EasyTom L or the EasyTom XL, so you can see the sizes that we can handle in these systems. Also, with going to bigger systems, it also allows us to use different configurations inside of the machine. So in this case, we have a 150 kV generator in the small system. If we need to go on higher energy sources, then we go also to bigger systems. The bigger systems also allows us to go to higher resolutions. So it depends on the configuration and on the application that the customer needs. So these systems, these three cabinet systems, they are fully protected by LED. So the protection towards the operator is fully integrated into the system. Then we have the fourth systems, which is on the list, which is the UltraTom, which is actually a system that needs to go inside of a bunker. So in that case, we will construct a separate room inside of a building, which is providing the protection for the operator, and we put this system inside of it. Here are some references in the industrial sector, so just to show that it's a very broad, the type of application that we touch. It can be anything from medical to cosmetics, a lot of automotive, of course. There is some aeronautics, so it's the type of applications is quite broad, where we can use CT. So now I'll continue with a whole bunch of examples of applications where potentially we could use CT as a way of checking samples. So these are let's say the main areas where we use CT. So general industrial components that can be checking for porosities inside of die casted parts, for instance. General metrology. so checking dimensions, especially for samples where we have difficulties to reach certain areas where it's on the inside, or maybe for 3D printed parts where we make complex shapes that we cannot measure with conventional technologies. Anything which is additive manufacturing, where you want to check if the sample is printed correctly, if there's maybe some areas where there is material not welded correctly, or areas which are not possible to measure with conventional technologies. Anything which is assembly control, in this case it's a medical cap to see the interaction between the different plastic components. Material research, in this case that's a foam, where they want to see the different structures of the cells inside. So on a material really high resolution level. Next is electronics, so checking the inside of the different components to see if they're in the right space, if all the connections are made correctly, etc. Anything related to composite materials is also an interesting field, where we check the porosities inside, if there's certain fiber directions, if they're oriented in the right way, and so on. And then everything which is more on the academic side, where they're checking biological samples, can be dead animals or bones, or it can also be rocks or other biological samples. Some other examples on first on the radio side. So without doing the 3D scan, we can just do some checks in radio mode. That can be as easy as looking, is there a cable missing, or is there a screw inside or not? So that kind of things. So in this case, you can see on the left there is an electrical engine where there is a wire missing. Or on the right, you can see a circuit to see if the tracks are in the right spot, if there's maybe something missing, and so on. So no need to go to 3D. In 2D, we can already see plenty of things. Here is another 2D view of a phone. So with the battery taking a lot of the space. And on the right side, a more zoomed in 2D view on the bondings on a certain area of the phone. So we can zoom in and have more detail. And in this case, we can actually see the porosities inside of the bondings. In case we need more detail, we go to 3D. So this is an example of a plastic welded pipe. In this case, we want to see the area which was welded to see if there's any leaks potentially. At the same time, we can see a lot of porosities that happen during the welding process. On the top left, we can also see one of the gaskets sitting inside of the sample. So a lot of different things to see in one scan, let's say. Here is another example of a aluminum die-casted part to check for porosities, certain zones which might be not as dense as they should be. Here another example of a steel weld to check the porosities inside of the weld. Typical application. Here we have an analysis of a plastic bottle. And more specifically, the customer here wants to see the distribution of the wall thickness. So instead of cutting the sample up and measuring the wall thicknesses, we're going to scan the sample, and we can, in one view, with this specific analysis software, we can see the distribution of the wall thicknesses along the sample. So every color represents the wall thicknesses, and in one view you get an idea of how the plastic is flowing and if they potentially need to change the parameters of the injection process. Same part, so in this case we took a bunch of points along the wall and measured precisely each of the thicknesses. Here is again on a plastic bottle with different layers. You can see you can measure actually the different materials inside of the wall thickness, let's say. The medical cap, so again to check the assembly of the part. In this case a 30 micron scan to check if the interaction between the different components is correct. You can see in some areas also the liquid present, so which is giving a different gray value compared to the plastic. Some scans on soft materials, so this is a scan of a shoe, so you can check the different layers inside, if there's potentially porosities inside of the sole. So quite a lot of information in one view, let's say. Then another example in additive manufacturing, where we're going to analyze the powder which is used for the printing of metal components. So in this case we are visualizing the different powder particles, so we can measure them, we can check if there's porosities inside, so it helps us to understand the distribution of the powder. An example of a composite material, so aluminum matrix. In this case we have a very high resolution scan. As you can see, for high resolution scanning we also use very small components because we need to go very close to the source. So we can't do high resolution scanning on big samples. We need to reduce the size of the sample. And in this case, yeah, you can see the orientation of the fibers, you can see cracks, you can see the binding material, etc. Another example of a rubber hose, where we want to visualize the position of the reinforcement material inside of the rubber, to see if it's well placed, and potentially measure the thicknesses of the rubber. Here an example of metrology application on an assembled part. So in this case a phone, where we can see the different components. So looking at the image on the right, you can see that there is different gray levels between the components. So just to give you an idea, that the bright white is steel, the somewhat brighter on the left is aluminum, and then the lower grade gray is plastics. So this gives you an idea what the different materials look like, so they get a different gray level based on the material density of these components. But we can use the different components still to do measurements between the different materials. Same example, so you can start measuring the different dimensions between the different components. Another example of connectors, where they had some pins broken, so without disassembling the parts we can see that something is wrong. Some earphones, looking inside, the capacitor inside to see if there's no gaps inside of the roll. A 2D view of a battery pack from a laptop. And then we can start making 3D scans on specific regions of interest and start visualizing it in 3D as well. An example of another composite material where we want to check the orientation of the fibers. So this is again a relatively high resolution scan where we want to see the flow of the fibers inside of the material. And then we have an example of a production application. So this is for dental implants, where they want to check if there's any porosities inside of the dental implants. And so we scan a whole bunch of these samples together, so we can put up to 80 parts inside of the machine, scan them all together, and do the analysis, so the porosity analysis on the full stack of samples, and make sure to take out the bad ones. Okay, now we're going to show the system how it works. So I'll present the full flow from doing the acquisition, so creating the 2D images, up to the point where we have the 3D model. So today we'll use just a plain bottle as an example. So first things first, we're going to put the sample inside of the machine. So it's important to make sure that it's nicely centered on the rotation stage. So that's the first step. Then we're going to close the door. And we're going to put on the X-rays. So what we see is the bottle in radio mode. So what we can do now is start looking at the sample in live mode. So we can start rotating it, zooming in. So in some cases it might be interesting to see at the location of certain features. And then we start putting the settings for the 3D scan. So if needed, we can take these images as they are, export them. First off, I'm going to make some changes to the settings. There we go. We need to make sure that when we rotate, that the sample stays nicely in the field of view, that it doesn't go out. So this looks good. In this case, we have a 10-minute scan at 25 micron resolution. And once all the settings are good, I can say, okay, let's go. First, the system asked me to remove the sample from the field of view and started tomography. So now it'll first do a calibration of the detector. So it means it's going to make sure that everything which is black and everything which is white is white. So that's what he's doing now. Now he's creating the black image. So now he's going to put on the X-rays again. He's going to wait for 10 seconds. And then he'll create the calibration for the white. And once this is done, it'll bring back up the sample and it'll do the 360-degree turn to create the images. So in this case, we will make 1440 2D images that we will afterwards use to create a 3D model. So there it goes. It's back into the field of view. And now it started to make the 360-degree turn. And during this time, it's taking the 1440 images. All right, so the scan is almost finished. It's at the end. So it will turn off the X-rays automatically. It's saving the data. And we can open the door again, remove the sample and put the next sample if needed. Okay, so once the scan is finished, all the data, all the images will be sent automatically to a second PC. So we have a first PC which is connected to the system, which is the acquisition PC. The scan data itself will be sent to the second PC, the reconstruction PC. And this we will now explain how we, from the 2D data, so the X-ray images, we go to a 3D model. So this is all the images that we created just before. There we go. So it's loading everything. First step is to reduce the size of the box. So everything within this box is actually data. So everything which is air we don't care about. So we're going to crop it out and make it and reduce the size of that volume. Then there's a whole different type of filters that we can apply to improve the quality of the images. And then at the end, once we applied all these filters, we can ask the software to reconstruct the volume. So now he's gonna, with specific algorithms, he's gonna calculate it into a 3D model that we can use afterwards to do measurements and other type of analysis. So depending on the type of scan, it'll be between a few seconds and a few minutes time to do the reconstruction. Okay, so the reconstruction has completed. So what we see here is a view. So we have the 3D model on one view, and we have a section view on the other three views. So we can actually effectively walk through the sample in the different views. We can actually increase maybe the contrast between the different materials, makes it a bit more visual. And so now you can use this to do your first analysis. So if you're looking to do more assembly analysis, this data is already very useful. So you can start looking on the different cuts. You can stop. You can start zooming in on specific views. You can also do some basic measurements already. So if you want to know the thickness, or you want to know the gap between two different components, so that you can do already. If we want to do more advanced analysis, so this is our own RX Solutions software to create a 3D model. Now, if we want to do a next step and let's say do more advanced analysis, we go to third-party softwares that are specialized in specific type of analysis. So once the 3D model has been created, we will go to a third-party software. Depending on the application, on what the customer exactly wants to analyze, we will propose one or another software. In this case, I'm going to show VG Studio Max, which is software which is used a lot for industrial applications. They have different modules. It can be porosity analysis, it can be CAD comparison, wall thickness analysis, or general metrology measuring. So we can manipulate it like a 3D model, like a CAD model, but this is the actual scan part. So we have quite a lot of detail inside of the scan. So now we can start using this 3D model to do certain analysis. You can potentially start just clipping and looking at certain sections. In this case, I think we can maybe first look at a porosity analysis. So this was an analysis done here. So you can see in this case, it's showing all the porosities with a different size, with a different volume. So everything which is blue is a certain size, certain volume of porosities, depending on the color. So we can also see it in 3D here. We can make it transparent, so 50% transparent. In this case, we can see all the different porosities inside of the sample in one go. We see here there is a bigger combination, which is making one big porosity. We can, for instance, start doing some measurements. So I'll take away the porosity. So first things first, we need to create some planes. So I'll take this screen. We're gonna create a plane. So let's say that this is a reference plane. There we go. I'm going to create another one on the other side. There we go. We could potentially also create a cylinder, so on the inside here. So the software will automatically calculate the cylinder inside. There we go. So we have a couple of different geometries, and now we can decide to measure certain distances between these. So if we say plane 1 and 2, we want to know the dimension between it, so we can create it. So in this case, it's 24.92 millimeters between the two planes. So you can create a full template on top of this 3D model that you can afterwards use on other 3D models that will be scanned afterwards as a template. Okay, so that was a brief overview of how the full flow of scanning a part looks like. So I hope you've learned something about CT, and yeah, let's go to some questions.